All right, let's share the screen and get this chapter going. All right, I assume you are recording. Yep, we are recording. Sweet. All right, welcome to chapter 27, Optical Instruments. This is an extension from chapter 26, which was all about lenses and how they function and images, how to measure them, things of that nature. This is the practical application of that last chapter. We're going to talk about optical instruments. You are familiar with these from your other science classes. This is going to be how they work on a physics level, how the magnification or what have you actually works, not necessarily how to use the actual instruments. That would be a lab practical more so than this particular chapter. So, what optical instruments are we going to talk about? Well, we're going to talk about the human eye. We're going to talk about corrective lenses, corrective optics, magnifying glasses, microscopes, telescopes, and finally, lens aberrations. To start out with, let's talk about the human eye and its use as a camera. So, with the human eye, light passes through the cornea. That's the front part here, the part that bubbles out of your eye, and is focused by the lens of the eye that sits within your eye itself. The lens sits within the eye, cornea is where the light goes through. The ciliary muscles change the shape of this lens so they can focus at different distances. So if you've noticed, you can focus back and forth with your own eye. That's because your eye itself is adjusting a little lens within inside to cause that to happen. Not a biologist, so if I screw these up, the vitreous and aqueous humors, I'm going to assume those are what those are called, are transparent. These are the things that, like the fluid of your eye necessarily, the aqueous being on the outside between the cornea and the lens, and the vitreous being the internal of your eye. And then at the back of your eye, you have rods and cones, which I'm sure I've heard of before, that convert the light that enters the eye into electrical impulses, which then travel through your optical nerve to your brain, allowing you to see. That's the super, super basics. I'm breezing through this parts of the eye. So the eye produces a real inverted image in the retina. Why don't things look upside down to us? Well, because the brain knows the eye produces a inverted image and adjusts it accordingly. As you can see here, the image is that large purple triangle outside the eye, and then what is shown on the eye through the cornea and the lens is inverted and of a different size, and the brain then adjusts it back and forth accordingly. And as I said before, the muscles that control that lens dictate what you focus on, so much so that you can look at something near and something far, and they are both being the same detail. The near point, let's talk about what a near point is. The near point is the closest point to the eye that the lens is able to focus. With normal vision, it's about 25 or so centimeters from the eye, but increases with age as the lenses become less flexible. So that's losing eyesight, is losing your near point. The far point is the furthest point at which the eye can focus. It is infinitely far away, and that makes your vision normal. So you can focus on something really, really far away, you have quality vision. If you have issues with that, then you have problems usually with the lenses contorting the way they should, and you have worse vision. A camera, a classic, well, any camera really, but this uses a film camera as an explanation. A film camera essentially works in the same manner. However, a camera's lens cannot change its shape because it's a piece of glass as opposed to what we have in our eyes. So the lens itself will move closer to or further from the film in order to get that focus. When you adjust your camera's focus, you can actually physically see the lens moving back and forth. The F number given on those lenses, all major lenses have an F number, is derived from the focal length of the lens divided by the diameter of the aperture, capital D. These two numbers provide the math for the F number. And the combination of F number and shutter speed, which is how long the light hits the film or whatever film sensing material your camera has, determines the amount of light that reaches it. and gives you the picture in whatever form you want, the picture in a fuzzy, the picture crisp, or what have you. So our lenses in our eyes slowly lose potency over time, which causes people to get corrective lenses and optics to fix that. In a two-lens system, as shown here, the image produced by the first lens serves as the object of the second lens. So you can see that bright red arrow to the left of the first lens, and then the duller-looking arrow to the right produces the image that the second lens there transports through. So these two work in conjunction. The second lens only sees what the first lens lets through. To find the image formed by combination of lenses, consider each lens in turn, starting with the one closest to the object and moving backwards. The total magnification is the product of the magnification of these lenses. So, a nearsighted person has a far point that is a finite distance away. Objects further away will always appear blurry. This is due to the lens focusing too strongly so the image is formed in front of the retina. So what happens here is if you have nearsightedness, when you try to look at something, the object itself doesn't, your eyes can't focus correctly enough to bring that object, to bring the far point at the point of that object. So the issue you have here is this is kind of cool when you look at it, the ray tracing of the lens itself, the ray tracing off of that object through the lens does not drop the image created perfectly on your cones and retinas. It drops them either before or behind, which we'll get to, causing a less crisp image than your brain has to translate that. Correcting this, you get eyeglasses, right? A diverging lens is used. Its focal length is such that the distant object forms an image at the far point. So the lens takes the rays from the object, bends them wider so that your eye can then narrow them down on the cones and retinas that they need to be narrowed down to. The strength of corrective lenses is usually quoted as refractive power, which is the inverse of the focal length. 1 over the focal length gives you refractive power, gives you your diopter in 1 over meters. A person who is farsighted, versely, sees, well, the same problem in an opposite way. Namely, instead of the image in the eye being formed in front of the rods and cones, it's formed behind them, so it actually hasn't coalesced together, again, giving you a fuzzy image. And correcting farsightedness, use a converging lens, because what that does, it takes the image and it squishes it down a bit more, such that it will focus itself perfectly on your rods and cones, allowing you to read. That's eyeglasses, that's corrective lenses. Let's talk magnifying glasses. A magnifying glass is a simple convex lens. It works in conjunction with the eye to make objects appear bigger as they be. It makes objects appear bigger because it makes them appear closer. There we go. Sorry, my bad. I misspoke there. Similar to corrective lenses for farsightedness. So they're basically big corrective lenses. The angular size of an object is the angle it subtends on the retina and depends both on the size of the object and, of course, the distance from the eye. The closer something is, the bigger it appears because the closer it is, right? Or the larger it is, the bigger it is. Magnifying glasses cheat that idea using these equations here. The angle, assuming it is small, is given by the height of the object divided by the distance from the eye. If the object is moved closer, angular size increases. And if it's placed in the near point, its angle is shown below, where the height of the object divided by n. So, if we place a converging lens whose focal length is less than n, we get a larger angular size of the object. Therefore, the object appears bigger because you essentially brought it closer to you. The lens creates an image of the object that's closer to your eye than the object itself. And this angular magnification is given by theta prime divided by theta, which is given by a relation of n the distance and f the focal length of the magnifying glass. All these equations come together. That angular magnification equation should be in this list down below. And it allows you to relate the differences in angles to focal length, magnification, heights, whatever you really want it to be. The magnification can be maximized by having the image at the near point. So since this is a lens, this lens has a particular location compared to the distance of the object and your eye, that will be maximum magnification. You go past that, you get fuzzy, you get closer to it, you're not quite as magnified. That near point is shown here given the magnification focal length, as I said previously. That is a magnifying glass. Let's talk about a compound microscope. A compound microscope has, in its simplest form, two converging lenses. One at the eyepiece, close to the eye, and the other is close to the object, right? You, again, in your lab practicals, this should sound familiar to you, although we don't use mirrors necessarily as much anymore. So when the object is placed near the focal point of the objective lens, its given magnification is shown by this top equation here. Di over d naught, the negative of that is equal to the magnification of the object, which is about equal to di over the focal length of the object. The image formed is at the focal point of the eyepiece, which produces an image essentially at infinity. So your total magnification of your compound microscope is given by the play of these eyepiece and objective lenses. We've talked about how these lenses work in the last section. Multiply them together, essentially, right? So your distance of your object and the distance of the eyepiece and the objective lens cause the magnification that you're talking about, the total magnification. And so when you use a microscope, when you crank it around back and forth, you're adjusting the objective or the eyepiece lens around. If you switch lenses, you switch objective lenses to get closer, right? That causes, when this is in good harmony with what you're looking at and the strength of the individual lenses, you get a nice, crisp, clear, very zoomed in image. The math kind of looks complicated. It's really not. It's got more subtext than actual letters, as you can notice, just objective and eyepiece. It's not really that scary when you get down to brass tacks and do the math behind it. So we talked about microscopes, which zoom in on something really small. Telescopes, similar to microscopes, have an objective and an eyepiece lens. However, the objects observed are essentially at infinity away, very far, right? So the light will be focused at the focal point instead of the near point of the objective. The objects themselves tend to be very large, but their angular size is very small due to great distance. So it is, in one argument, the same conversation, and in another argument, a completely different conversation. And again, this should kind of look familiar, right? This is objective eyepiece working together to take the object, expand, and change around its angles so that it looks good in your eye and is focused in your eye. Now, this stuff looks very similar to me. It should look similar to you as well. Your total magnification is, of course, given by the focal lengths of the objective and eyepiece, which in those focal lengths give an angle from the rays of the light. The telescope uses lenses called refractors. First telescopes were of this type, refractor telescopes, also reflector telescopes, and those compound telescopes. Big old huge world telescopes, super fun to get into. I suggest it. You kind of get hooked. And it's really not that expensive of a hobby. You just need nighttime, right? It is desirable to have the objective of a telescope be as large as possible, so it collects as much light as possible, right? Each doubling of the diameter of the object gives 4 times that much light. This has to do with R squared and stuff like that. It's commonly shown in equations. Point is, the bigger something is or the closer it is, the more you can zoom in on it, right? It's a lot easier to look at the moon than look at Jupiter with your Walmart telescope. Very large lenses are difficult to handle. They're thick and heavy, must have too precise surfaces. So very large lenses are used at observatories you really can only get such a certain size of telescope at home before the math about using these lenses gets out of hand. Large telescopes are made as reflectors as opposed to refractors. The object is a mirror rather than the light, right? The objective, sorry. The mirror only has one surface, so the light can be made very thin and reflects almost all the light that it hits. So what you have here is you have, instead of adjusting a objective lens, you have your self-object moving mirrors back and forth that do the same act as we've been talking about, of bending the ray traces down so that they focus exactly where you want them to focus for your eyepiece. But you're using large mirrors instead because you're reflecting rather than refracting the light. And again, if you want to get in telescopes, feel free to get into it. In this class, we don't dive into that too deep, but it's a fun can of worms. Lastly, let's talk about lens aberrations. Spherical aberrations occur when light striking the lens far from the axis does not focus properly. This can be done by grinding the lenses to fit what it wants. But what you have here then is the particular angles at which the light hits causes all the light that enters to not focus at the same location, giving you essentially two focal points, thereby creating a fuzzy and gross image. Chromatic aberrations can occur as well. If you have a material that will reflect different colors differently, a prism essentially, you can be looking at purple and be seeing red and blue and be out of focus, right? I believe this is how old-fashioned 3D glasses work. Well, this now is how old-fashioned 3D glasses work, I should say. So you have these chromatic aberrations. What you do is you use more corrective lenses. You can bend and change a lens based on its angles, based on its degrees, to bend light however you want because it follows these simple mathematical formulas. So you don't have light working the way you want, put some glass together, fix that problem. And it's all, this math is basically keeping your angles the same. So that was chapter 27. Very breezy, I know, very easy. I just wanted to go over these lenses for your practical application of what's going on. In summary, human eye is focused by muscles that change a lens. However, since we can't build fleshy lenses, we build lenses out of glass. Instead of having muscles for instruments, we have to move lenses back and forth in relation to each other. Diameters and focal lengths come into play at this point. Nearsightedness and farsightedness are fixed by glasses. If that's new to you, I'm very shocked you've never heard that before. Sorry. Here we have some very simple equations for comparing focal lengths to magnification, ends, distances, things of that nature. Compound microscopes have a certain equation to them. Telescopes have a certain equation to them. These are basically the same equation because microscopes, telescopes, magnifying glasses are all various ways to organize the exact same pieces. Lens aberrations happen when, well, your lens isn't right? If you've wore glasses, you know that as your vision changes, you need to update your prescription, get new glasses. That should be unsurprising to you. So that's in chapter 27. That's that very, very brief chapter. And I hope you enjoyed watching it. Leave any comments down below. Have fun with your homework. Stay safe and take care.